Hello. This is a recording of a talk of a result that is about to appear in ESA, and it's a joint work with Timothy Zhou. I think it might be better to think about it as an active survey. We survey the known results in this subfield, and we derive some new result by making some observations, and that's our contribution to some extent. So it all begins with a center point. So we have a point set of endpoints in the dimensions, and a center point is a point that is in the middle of the point set, right? So if you have points in one dimension, being in the middle is very easy. It's just going to be the median. But center point extend these notions to higher dimensions. The idea is that a point is an alpha center point if any half space that contain it contain at least alpha fraction of the points of the point set. We will see an example shortly. And it's well known from the 30s that there is always a 1 over d plus 1 center point in the dimensions. And a natural question is to ask how good is a center, how good of a center is a given point, right? So I give you a point, like this red point in this slide, and I go to all the half spaces that contain it. I might as well take the half space that concentrate only on the half spaces that pass through it. For each one of them, we can ask, okay, how many points are there? And then look for the half space that contain the fewest number of points. And this determines how good of a center point this point is as far as this fraction of this number. So as I just mentioned, this is going to take us roughly n to the d time to compute for a given point, which is quite slow. So in fact, it's an open question how to compute a good center point in polynomial time in d. In particular, it's known that you can do it in n to the d minus 1 times in d dimensions. Since we cannot get really an exact algorithm in polynomial time in d, people looked into approximation algorithms, and there is a result from the 90s that gives an approximate center point in time polynomial in d. So the running time is good. The approximation is not great. It's roughly 1 over 4 to the d squared. To remind you, the best center point is roughly 1 over d. So there is a big gap by a factor of d between the approximation and the best that exists. And recently, we slightly improved the quality of approximation and the running time. And as I mentioned earlier, even if we use those algorithms to compute a center point, how can I prove to you in a compact way that it's a good center point, right? Of course, you can just believe me, but if this is not enough, you might want a proof. So there is a very nice result of Birch from 1956. This is one of those results that are known and unknown, in the sense that the result is, of course, well known, but somehow it's not mentioned in previous work somehow. It's cited in some of them. So Birch showed that you can find, there's of course, in two dimensions there is always a third center point, right? So there is a point that contains a third of the points for every half space that half plane that contains it. But you can do much better than that. You can compute a partition into triangles of the point. So you partition the point into triples. Every triple is a triangle, such that the intersection of the triangles is non-empty. And this is your center point. The reason why it's a center point is because every half plane that contains the center point must contain at least one vertex of each one of those triangles. So as such, it's a third center point. So we revisit this result. We provide an n log n time algorithm because Birch didn't really provide running time, but this is a minor contribution. Of course, the reason why Birch theorem is relatively forgotten is because roughly 10 years later, Tverberg came up with his amazing theorem. So Tverberg theorem states that if you're in d dimensions, you can always partition the point into group of size n over d plus 1, such that every d plus 1 form a simplex in this partition, so that the convex hull of all those sets in the partition is non-empty, right? So this, essentially you partition your points into simplices, and all the simplices have non-empty intersection. Essentially, this point of intersection is the desired center point, and the proof of the theorem is quite beautiful. It's a constructive algorithmic proof, but the running time is pretty awful. It's roughly n to the d squared. We revisit this proof and we provide explicitly the running time analysis. Again, this is not really new. So the natural question to ask is, can we do approximation? Especially, what can we do with polynomial time in D? And here is the table of the non-results. So there is quite a bit of work. I would say the two most relevant results for our work is the result by Miller and C and Mulzer and Werner. I'm not going to go through the table, but roughly you get the same gap we had before, right? You can get roughly n over d squared point of this depth with a compact proof, but the running times are not quite polynomial. Rolnick and Souberon provides a running time which is weakly polynomial, but the constants are not great. So what we do in this work, we improve all the results below the double lines in this table. But how do we improve them? We improve them by taking those previous work, chopping them into parts, gluing them back together in a different order, and stuff like that. And the other thing we do, we make a relatively simple observation showing that in fact you can get a strongly polynomial approximation for Tverberg point, which I think is quite interesting. Okay, so here's a table of our new results. Going through this table is too overwhelming to really do it during a talk. I think that, as I mentioned, the main result is a second result here that gives you a partition that is a Tverberg partition, and the depth is roughly n over d squared log d. If I had to pick one result that is a significant step forward in what we know about this problem. But as you would see, this follows from an easy observation. The other results, as I said, are by combining previous works and pushing the techniques a bit further. Maybe another interesting application of our approach is that we were interested in what can be done in near linear time in low dimensions, right? So even in 3 dimensions, we know that there is a point with Tverberg depth n over 4, but we don't know how to compute it efficiently, not even remotely, right? So we show how to get an n over 6 approximation in linear time, and the previous best result known was n over 8, and we get similar results for dimension 3 to 8. At 8 dimensions, we're essentially losing to what was known before. So improvement only for dimension 3 to 7, which is hopefully interesting because in some sense, if you have to use it in practice, you would probably try to use one of those approaches. Okay, so it turns out that the trick, or if you want the backdoor to those approximation algorithm, both for the center point and the Tverberg partition, is Radon theorem. And Radon theorem states that for any set of d plus 2 points in d dimensions, you can partition them into 2 sets such that the intersection is non-empty. This proof is very easy in the plane. You just look on 4 points. Either they form a triangle with a point in the middle, then you just partition them into the 3 points and a point in the middle for the 2 sets. Alternatively, they form a quadrilateral, but then you just take the 2 facing diagonal, the 2 pairs that form the diagonals, and they intersect in the diagonals. And by the way, you can use this proof to extend it to a higher dimension using induction of the dimensions, but a more natural proof is in fact, or a more useful proof is the algebraic proof. And it turns out that computing this point of intersection boils down to solving a system of d equalities in roughly d variables, and it can be done in cubic time using Gaussian elimination. And this also gives you the partition. And this is really important because this intersection point intuitively is already a better center point than you had originally has, because it's included in 2 convex hulls, which means that any half-plane that contain it must contain at least 2 points in 2 dimensions. Okay, so what did Miller and C suggested to do? Well, the basic idea is to now start merging covers, right? So what do I mean by that? Let's assume that you have 4 points. Each point you have a cover by 2 triangles, right? Now we are in this setting where we have the proof, right? I'm claiming that the point have a certain Tverberg proof depth, and I'm carrying with me a set of simplices that contain this point as the proof, right? So I have 4 points and I have the proof in 2 dimensions. If I take those 4 points that are being covered, then by Radon's theorem, there is a point in the intersection of the convex hulls. So now I can go back to the covers and take, for example, the blue triangle from above, or the red triangle from above, and the red triangle from the bottom, and combine them to get a red set that its convex hull covered the purple point. So then I get a blue point, and now I can apply to the horizontal sets, right? So now I got, by doing 1 iteration of this Radon point, I found a new point that has depth 4, right? I started with point of depth 2, and I got a point of depth 4. And now, an important step now is to sparsify the representation, right? So the key observation is that for each one of those convex hulls, by Karator-Dowie theorem, there is a single triangle or single simplex defined by the vertices of this set that contains the point. So you do that, right? Now we have, again, a cover by 4 simplices, and all the vertices that point that we are not using anymore, we can throw them away. They are now free again, and we can reuse them, right? So that's what this algorithm does, right? It starts building cover up. Every time it merges cover to get a deeper point, it frees some of the point, it throws the points out back to the queue, and as point of depth 0, and the algorithm continues in this fashion. Merging thing, building higher and higher towers, and recycling points that are not used so that they can be used to building higher tower, until you get to the highest tower you can build in this way. And you get this running time written on the slide. It's a very nice algorithm. So it turns out that what we can do, we can take this Miller and C algorithm and think about the recursion tree that they get. They essentially get this huge recursion tree, which have super polynomial size because they're recycling points. And instead of the bottom of the tree of using Miller and C algorithm to build the small towers in the lower level, we're going to use a different algorithm which is faster but builds a low quality tower. So we can just use the result of Molter and Werner, and putting them together we get the best of both worlds. Right? We essentially get the quality of Miller and C, we get a pretty deep point, but the running time, we get the running time of the previous fastest algorithm. So that's good. Okay, maybe let's go back to the what I stated as maybe our main contribution. that is a strongly polynomial time. So the algorithm sadly is extremely simple and based on a very simple observation that if you just partition the point set into this number of sets, roughly every set has to be of size d squared log d, right? So you randomly partition the point set into this number of sets where every set has this size, right? So this can easily be done by random coloring, for example. It turns out because of epsilon net theory that it's easy to argue that the convex hull of all those sets are non-empty. Namely, we got a deep point, which is very nice. But the weird thing is that we know that there is a point in the intersection, but how to compute it, right? We just know that it exists. Computing it is too expensive because we don't really have a strongly polynomial time to compute it. So either we are happy with that. It turns out that you can trade another factor of d in the depth and now get a point in the intersection, which is kind of nice because this is the first strongly polynomial time approximation algorithm. Okay, what happens if we allow you weakly polynomial time, right? Then we can solve a linear program. And if we are using linear programming, then it introduced a new powerful tool, and in particular, Rolnick and Soberon had some nice results using essentially LP. And we are getting, by using ideas similar to them, we are getting also improved results, where again, the running time is weakly polynomial because we use linear programming. So the running times are stated on the slide. Essentially, we get the same approximation we got in the previous slide, roughly n over d squared, but the running time is d to the log d, right? Instead of d to the log d. So there's a slight improvement in the running time. Okay, so conclusions. So I think the major question suggested by the work on this problem and by previous work is why do we have this D gap between the true center point, the true Tverberg deepest point, and what we can approximate efficiently? So can we polynomial time compute better than 1 over d squared center point? And another thing that's very interesting is whether we can do come up with a better algorithm for Tverberg point, the exact one. Currently we have the constructive proof of Tverberg, but the running time is pretty awful. It would be nice to get something better. And that's it. Thank you very much.